Malaysia Green Building Council, also known as Malaysia GBC, is an organization that promotes green building programs, technologies, and design practices, aims to make Malaysia an eco-friendly and sustainability place on Earth. Malaysia GBC was founded in May 2009 by a group of passionate building consultants, academia, and representatives. Even since Malaysia's building has increased, the efficiency of resources used in each building was built with green in mind. Malaysia GBC is also supported and associated with most of the top industry institutions. In the year 2015, Malaysia GBC became an established member of the World Green Building Council and known to be the only organization in Malaysia to be supported by the World GBC. Malaysia GBC continues to be the platform that networks, promotes, educates, and most importantly, develops the sustainable, built into the land of Malaysia. With much more passionate industry professionals, we can make Malaysia a greener and better place on Earth.
Good afternoon, ladies and gentlemen. Welcome to IGN Pocket Talk. Today's session is a joint event of IGN and Malaysia GBC. My name is Tan Siti, the council member of Malaysia Green Building Council, and the moderator for today. Malaysia Green Building Council is a non-profit organization that promotes green building and sustainability. We are looking for greener industry players like you to join us to grow the green economy. Again, it's my pleasure today to welcome you here this afternoon to our webinar on wind-driven rain assessment, building toward climate resilience. Based on the webinar title, you might wonder, what is wind-driven rain? How can one predict the event of wind-driven rain? What are the parameters and mechanisms of wind-driven rain? What are the impact of wind-driven rain to the buildings? In today's Pocket Talk, we will find out the answer to those questions and how to design a resilient buildings to overcome the natural impact of wind-driven rain on buildings. Without further ado, let's welcome our speaker today, Mr. Campbell. Mr. Campbell is an Associate Director at Building Systems and Diagnostic Private Limited. He graduated from University of Kansas and practiced as an aerospace CFD engineer in USA for more than 5 years before returning to the Southeast Asia. He specialized in three-dimensional CFD analysis for the simulation of buildings, for the prediction of the thermal comfort, wind-driven rains, ACMV extract, and etc. Ken's track record in the built environment includes more than 200 CFD projects. He lectured on the topics of CFD simulation at Green RE accredited professional course and at Singapore Building and Construction Authority BCA Academic Green Mark accredited professional course. He is an external assessor for BCA Green Mark criteria and a member of BCA Natural Ventilation Task Force. Now, let us welcome Mr. Campbell. Over to you, Mr. Ken.
Okay, thank you. Let me share my slides. Okay, all right, good afternoon, everyone. My name is Ken. Thank you for joining the event. Okay, so for the next 1 hour, I'll be mainly talking about what is wind-driven rain and how it affects the building. Okay, I'll start off with very brief introductions to the company, BSD. BSD is actually a spin-off company from one of the research programs between Singapore National University and the Singapore Building Construction Authority. Since 2003, since our founding, basically we have helped with the building developers in the ESD, environmental sustainable design, right? So over the years, we have completed more than 500 developments throughout Southeast Asia. And that is our goal to help improving the energy efficiency of buildings, improve the thermal comforts, and to reduce the environmental footprint. So our primary service includes ESD consultancy, building performance modeling to help with the different green building certifications, inclusive of the Malaysia GBI, Malaysia Green RE, Singapore BCA, EarthCheck, Wealth, US LEED, MyCrest, etc., etc. Right. So other than green building certifications, we do a lot of the building performance simulations. That includes CFD simulations, energy modeling, daylighting simulations, solar and shadow simulations, etc. Right. Over the years, our company has been actively involved, teaming up with governments to conduct different research projects, such as the rooftop gardens in 2007, the cool pavement coating in 2008, to work with Singapore Building Construction Authority, BCA, to develop CFD simulation methodology, wind-driven rain simulation methodology, and thermal comfort criteria. Right. So we have an office in Kuala Lumpur, in Singapore, and in Beijing, China. All right. So what is wind-driven rains? Wind-driven rains, in one quick sentence, is the rain doesn't fall straight down from the sky. Actually, there is a horizontal components associated with the raindrop trajectory. So you can see in these pictures, I have two pink color lines showing the trajectory of raindrops. So it doesn't come straight down, right? So for building, especially sheltered areas, because the area is sheltered, by right, it should remain dry even in the event of raining. But we can see from this picture, these particular commercial buildings at ground level, this sheltered corridor is basically completely wet, right? So our goal here is to introduce the concepts and the theories, the methodologies on how are we going to deal with these wind-driven rain situations onto a building. Right, so here before I start the presentations, I have a few videos that we would like to play. Due to the lag, so I have the organizers to help me play the videos, and then I will do some explanations. Please help play the video, please. I think I'll need to stop sharing. Right. Yes. Okay, so in this case, you can see that there's rain penetrating into this commercial linkway area. I think there are a few more videos. Please help continue play that. Okay, so this is another zoom in angles. You can see there's a lot of rain penetrating into this area, and gradually there is ponding happening. Even though if you see at the edges of this sheltered walkway, there is a scuppered drain, but the scuppered drain is not sized adequately, and partially it's because there is some blocking of the scuppered drains, that therefore the ponding gets more and more serious, right? So these are the three videos that I would like to show you guys to illustrate wind-driven rains and how it impacts the building. Okay, so let me share my screen again. All right, so typically the traditional facade treatments that goes with a building to protect it from direct rain penetrations, normally it includes the awnings, retractable awnings, fixed horizontal overhangs, vertical drop panels, or louvers, right? So these are the typical types of facades elements. But the question is, how big should that be? Should these facade elements be? So during the design process, we have to figure out a way to help size these facade elements. And that would require some engineering works. So before computer times, in building industries or in built environments, if we want to try to get some sort of airflow solutions or wind flow solution out, we will, before computers, we will have to do wind tunnel testing. Now for wind-driven rain types of study, that means that to really find that out, either we have to build a mock-up, or in a wind tunnel testings, you have to spray some waters to sort of create like a raining environments to find out the rain penetrations. There is very little wind tunnels that would allow you to spray water droplets inside the tunnels. Normally, wind tunnels remain dry, and the goal of that wind tunnel is mainly just for the wind study and not for the rain. It's very expensive to conduct wind tunnel testing. There's not a whole lot of wind tunnel facilities in, say, Malaysia or in Singapore. Probably only a few universities have such wind tunnel models, and they might not even open that up for the public to use or for the business to do experimental testings. Right. So doing wind tunnel testings is not that feasible. So the next best solutions to that is to use computational fluid dynamic simulation, or CFD simulations in short, to conduct these wind-driven rain study. And that's primarily the focus of today's talk. Right. So before I go further, I just want to briefly talk about CFD, computational fluid dynamics. It is actually a branch of fluid mechanics that really studies the fluids in motions. So the first word is computational. So obviously it's computer based. So you're using the computers to crunch the numbers to find that solutions. At the beginning, the CFD was used primarily in the aerospace industries, starting in the 1960s, 70s, used by NASA. NASA has a lot of CFD codes to calculate the aerodynamics of airplanes. And then gradually, the use of CFD is further expanded to other industries, including mechanical, automobiles, oil and gas, chemicals, medicals, as well as building industries as well. Right, so just a few examples of the different types of CFD applications for different industries. The first one is an airplane, and used in the aerospace industries. That's what I basically do day in and daytime while I was in the US before, right? And airplanes running CFD simulations to find out the pressures acting on the fuselage or on the wings. In automobiles, in the F1, they would run a lot of CFDs to really optimize those fins, those spoilers on the F1 car, so that if you would turn the F1 vehicle upside down, it would be able to stick on top of the wall, basically, because there's so much downforce generated by those fins or spoilers on an F1 car. And that's why F1 cars can make such a tight turn at such a high speed, because there's so much downforce, and therefore the tire has enough grip to make such a tight turn. Yeah, so there is an applications of CFD on the automobile industry. In oil and gas, I mean, in all the pipes where the oil is being transported, they are also using a lot of CFD to do those engineering calculations. In medical industries, the blood flow inside our blood vessels, all that, nowadays, medical industry is using a lot of the CFD to help with the study. So we now come back to building industries. So for building industries, we mainly trying to use CFD as a tool to find out the motions of wind flow surrounding and inside a building. So the primary outputs we got up from any CFD simulations related to buildings would be the wind velocity, pressure, and temperature. So what I have here, the three screenshots: velocity, contour, velocity vector, and pressure contour plots. These are the types of the CFD results that we can get out from the CFD software. Then from there, you can find out the wind behaviors, understand how the wind behaves inside the buildings, and change your layout accordingly to improve the natural ventilation performance of these buildings. It is not to say that CFD is only good for natural ventilation's performance calculation. It is not. But in Malaysia and Singapore, in the tropical countries, it is a fact that we use CFD simulations heavily to help improve the natural ventilation performance or the NV performance of a building, especially if the building is targeting the higher green awards, say green RE platinums or in Singapore, the green mark platinums, then it is a prerequisite to conduct CFD simulations to make sure that the natural ventilation performance meets certain passing criteria. But it is not to say that CFD is only used for natural ventilations applications. We use that for mechanical ventilations study. For example, one of the examples for mechanical ventilations application is the hospital. At the rooftop of hospital, they will have a lot of exhaust fans. Say that the exhaust fan coming out from the operating theater, the exhaust fan coming out from those isolation wards. So the discharge coming through those exhaust fans, we can use CFD to find out if the discharge would or would not recirculate back into the hospital building air intakes. So that's why we can use CFD to help us find that out. For air conditioning CFD, we use that for clean rooms, for pharmaceutical clean rooms, for data center. There's a classic examples of air conditioning CFD simulations. If you are a fire safety engineer, then you would do a fire CFD day in and day out and submit the results to the, in Malaysia, there will be the bomber, in Singapore, the FSSD for submissions. Rainwater runoff simulation is something that also can be accounted for. But our main focus today would be primarily on the wind-driven rain simulations, WDR, short form WDR. Right, so you might ask these questions: how accurate is CFD simulations when you're trying to apply that to building industries? So here I'm attaching a few pictures, basically extracted from some books that shows basic aerodynamics, the wind behavior as it approaches the building. So these are basically experimental results, right? So from here, you can see when wind approaches the buildings, at certain height and beyond, the wind will be deflected upwards. At certain height below, the oncoming wind will be deflected downwards towards the ground. And of course, a building is not infinitely wide. Okay, so some winds are deflected to the left and some deflected to the right. So this isometric view, the left pictures basically shows the wind behavior as it flow past a building in isometric view. At the back of the building, you have that recirculation zones or the wake regions. On the right-hand side, that is a side view or a section view that shows how wind behaves. So these are experimental results. Here, the next slide is basically also from the internet. It's a photograph of how the clouds or the winds that flow past the high-rise building. So you can see that this is very close to the experimental results. Okay, then when it comes to actual CFD simulations, so you can see here a high-rise building, wind coming in from the right-hand sides, and then at certain heights and beyond, the wind is deflected upwards. So that height, that what we call a stagnation point, below the stagnation point, the wind would be deflected downward. So toggling between these few slides, we can really give us a feel that yes, CFD simulations can be accurate in predicting a wind flow behavior surrounding and inside the buildings. Right. Okay. So the objective of this talk basically today is to help quantify the followings at the sheltered spaces. Our focus is mainly on sheltered spaces because if by design the space is sheltered, then there should not be any rain penetration. It should remain dry during raining time. But in the event there is wind-driven rain penetrations, then using these wind-driven rain simulations, we will be able to quantify the depth of penetrations. From here, we can calculate and estimate the rainwater accumulation rate so that would help with the sizings, say, of the scuppered drains or the cut-off drains. And then we can also look into, say, your base design does not produce satisfactory results, and I want to incorporate certain facades elements. Then using the wind-driven rain simulations, I can examine its rain protection effectiveness to see whether there is a reductions in penetration depths, so on and so forth. All right, so here I'll talk about briefly the methodology that goes into a typical wind-driven rain simulations. Say I have a set of buildings, that's my main development, and that is located at certain areas with surrounding buildings. So in whether that is in natural ventilation CFD simulation or whether that is wind-driven rain simulations, because we are modeling the oncoming natural wind, therefore we have to account for the presence of existing surrounding buildings. Right. So in 3D CAD geometry, we are not just generating the 3D CAD model of your own developments, but we're also we are accounting for presence of surrounding buildings. All right, so on the right-hand side is an isometric view showing we have accounted for the surrounding buildings because surrounding buildings will deflect the winds, and therefore your simulation result by accounting presence of the buildings, surrounding buildings, it will be accurate, it will be realistic. So this is step number one. Step number two is for typical wind-driven rain simulations, you have to basically first run the natural ventilation simulations, the one I talked about. You have wind coming in from certain directions at a certain wind speed, and that wind speed is expressed as a return period. So I'm introducing this term called return period. Right. So from here, once we get these results, NV simulation results, we can then go to step 3, injecting the raindrops. Okay, so from an established natural ventilation simulation results, we will then manually say inject a bunch of raindrops so that it falls right on the buildings that we are analyzing. We don't really care if the raindrops falls on other surrounding buildings because that is not our area of concern. So we mainly focus on the raindrops falling right on top of our buildings of interest. Okay, so in a few slides, these are the basic methodologies and at the high level and introductions of that in the high level. Then I'll go into the more details of that. So you might questions, okay, we have to account for presence of surrounding buildings. I got that. But what is the extent of sizes you have to account? So using this as an example, I've say in the middle is a private condominium development. If I were to draw a line connecting the longest distance across this particular development, says the reference length is 168 meter as an example, then the presence of surrounding buildings based on the current green RE CFD simulation methodology, the radius of that would be 3 times the reference length. So the diameter would be 6 times the reference length, and that's about 1 kilometer. So this diameter is about 1 kilometer in size. And that is the extent of surrounding buildings that you would need to account for. And by doing that, the simulation results can be considered accurate and realistic. Right. So in summary, radius is 3 times the reference length. Right. In CFD simulations, what we are actually doing is we are actually putting in our generated building 3D models and the surrounding buildings model into a virtual wind tunnel. Right. So this green box measures 1.1. Okay, sorry, I beg your pardon. My bad. This one shows let's say that right in the middle is the developments. So we can either include surrounding buildings 3 times the reference length, or we can include the presence of surrounding buildings 500 meter north, south, east, and west. All right. So this 500-meter extension is in the Singapore Green Mark standard. So you based on the locations of the projects, based on the different criteria, you can adopt either the 3 times reference length or the 500-meter extensions. Now, all right. Then the next thing is from here, after you have accounted presence of the surrounding buildings, the next thing is you have to identify for wind-driven rain simulations the areas of concerns. Now, in this case, this is a SketchUp model of a condominium projects in Kuala Lumpur. Basically, in Malaysia, there are lots of condominiums that on level 1, that is the pick-up and drop areas, and then you have a few stories of multi-story car parks, and then your residential blocks are located on top of these multi-story car parks. So at the level 1 or at the ground level, sorry, in Malaysia it's called ground level, you have this pick-up and drop area. So a pick-up and drop area is an area of focus. Typically, pick-up drop areas or poodle areas is an area of focus for wind-driven rain study. Right. A second example is this is a school project. So in school, a school buildings, typically a primary or secondary school buildings, is multi-stories. You have the classrooms, and then outside the classrooms, you will have this common corridor area or linkway area. So for school projects, the area of focus for wind-driven rains, naturally, it will be on this common linkway or the staircase core areas. Right. For residential projects, other than the poodle areas on ground levels, at the different floor levels on the residential block itself, the common corridor, lift lobby area, for example, this particular a section view, isometric section views cutting across a typical residential tower block, you can see that the middle is the lift lobby area, and then it has opening on both sides. So the common corridor lift lobby area, the design has the architectural design features good cross ventilation performance because wind can come in from one side and exit towards the other side. So it's not stuffy. That's very good for normal day situations. But in wind-driven rain simulations, in wind-driven rain situations, we will need to make sure that the facade elements, for example, in these examples, there is a horizontal RC canopy, and on the outer edge, edge of that RC canopy, there is a vertical louvers, whether these combinations of facade treatments, is it adequate to give good enough protections to this lift lobby area? Right, so that's another example of that. For commercial buildings, say commercial buildings with some outdoor refreshment area, Starbucks, those kind of dining area, it is sheltered area, definitely. Those with outdoor refreshment area is sheltered, but because they are located very close to the edge of the building, during raining time, would rain penetrate or would rain hits on those ORA areas or not? Right, so this is another examples on the commercial building types. Lastly, for using an industrial building, say I have an industrial buildings, a naturally ventilated industrial building types, inside my production areas or inside my functional space, these industrial buildings have fixed facades, fixed non-operable facade elements. Right, so it might features either a single band louver or a double band louvers. So it's not operable, it is not fixed. Then the next question is, would rain penetrate into my production area? Right. So you can see that in all these different area of concerns, I did not mention anything about residential dwelling units. First of all, residential dwelling units features operable facades, windows, either a casement, sliding, top hung, or the conventional lowered windows. So they are operable. Secondly, because they are operables, the tenants or the people staying in the dwelling units, residential dwelling units, during raining times, they will go to the windows and close it up to make sure rain doesn't penetrate. Right. So all the five typical area of concerns that I've highlighted deals with something that is fixed. If you have some facade treatments, or that facade treatments of facade elements, they are all fixed. So you cannot really improve the results, improve the rain protection effectiveness. Now, so primarily, realistically, a wind-driven rain simulations is more applicable to those areas that have fixed facade elements. If you do have an active system, say at the switch of a button, say the louver angles can be adjusted, or say the windows can be mechanically controlled to switch off at the push of the button, then an active system would be the best. If you do have an active system installed or provisions, then yeah, you are right. You do not need to conduct wind-driven rain simulations because you have an active system. The primary reasons we are doing this simulation is because most of the buildings would not have such an expensive active system. Okay, so the next thing is, after identifying the area of concerns, the next question is what wind directions and what wind speed magnitudes you are going to prescribe in your simulations. So for Malaysia, in Kuala Lumpur as an example, depending on your locations in the Klang Valley, you would either choose the Subang Airport weather data, or you would choose the KLIA weather data. If you have a project in PJ, Subang, or even in downtown KL area, say Bukit Bintang area, you are actually located, Subang Airport is actually located closer compared to KLIA. And therefore, you should always choose the nearest airport. So this is what we call a wind rose. I break it down into 12 different months, starting from January all the way to December. So what it says is a wind rose gives us an indications the prevailing wind directions per month. So in January, you can see most of the winds are coming in from the northwest directions. So northwest, west towards northwest, is primarily the prevailing winds recorded at Subang Airport from January, February, March, actually all the way to May. In June, we have more or more south-southeast winds or southeast or south-southeast winds coming up. That's in June, July, August, and September. And then in September, we have more northwest wind coming back, September, October, November, and December again. Right. So in summary, if we were to plot an annual wind rose of Subang airports, we can basically conclude the prevailing wind directions are northwest with an annual hourly mean wind speed of 2.09 meter per second. So that can be calculated. This is based on a 5-year sample. January 2012 to December 31st, 2016. So it's a 5 full years of data. And the next second most predominant wind directions would be the south-southeast or south wind with the annual mean wind speed of 2.65 meters per second. So if you were to conduct natural ventilation simulations or wind-driven rain simulations for your projects in KL or PJ area, I would strongly advise to use Subang Airport data. Then if you were to have a project, say at Cyberjaya or Putrajaya nearer to KLAA, yes, then you would use the KLAA wind rose data. This one is on the right hand side. So you can see that KLAA versus Subang airports, probably the distance between them is 50-60 kilometers apart. But you can see the wind rose is completely different. For KLAA, the predominant winds are northeast and southeast, versus for Subang Airport is northwest and south-southeast. Right. So depending on your project site, say at Bukit Pindang area, it's only 20 kilometers away from Subang airports. Well, if you compare that to KLAA, that is about 45 kilometers away. So you will pick the nearest airports. That should be the way to go. And we will always pick an airport wind data. For different buildings, before I continue further, for different cities in Malaysia, say in Penang, say in JB, say in Kuantan or Kota Kinabalu, KK, you would use the local airport wind data. That would be the best and most accurate way to do the simulations. Okay, all right, so that is for different airport data to pick from. Then the next thing is what would be the wind speed magnitude. So here I'm showing you the average wind speed from the Subang airport. So if we were to break it down into 8 different wind directions, here the occurrence percentage of year, that would give us an idea the percentage of times of that particular wind direction. So the calm wind accounts for about 13.5%, and north and northwest winds 13 and close to 20%. Southeast and south is about 9+% each. So these 4 pink color highlighted wind directions are the prevailing wind directions at the Subang airports. North and northwest winds are the prevailing winds during the year end, September to the May, northeast monsoon seasons, or when it starts switching to the northeast monsoon seasons. And then south and southeast winds are the prevailing winds during the mid-year southwest monsoon seasons. Right. Okay. So, but these are annual average wind speeds. So this would be good if you were to do a natural ventilation simulations. But if you were to conduct a wind-driven rain simulations, we would not use average wind speed. This is too low. So the wind speed is too low and it doesn't really reflect adequately the severe wind conditions. And therefore here I'm introducing this term called return periods. Okay, return periods expressed in months. What it shows us is see the same 8 wind directions from north, northeast, all the way to northwest. A return period, in a layman term, it means the wind speed magnitude that would likely to occur once in how many months. So if we take north wind as an example, a 12-month return period means this 6.59 or 6.6 meters per second of hourly average wind would likely to occur once a year. So that's what a return period means, literally. So for different wind directions, the return period magnitude for different wind directions, they are completely different. So you can see that the northwest wind is the highest at 7.95, and the east wind is the lowest at 5.12. So all these data, the return period table, are derived based on the original wind data, hourly wind data from the meteorological stations at Subang Airport. Okay, then the third one, after the prescriptions of wind directions and wind speed magnitude, we now go into the raindrop sizes. So when it rains, there are different raindrop sizes. You can have the very small 0.02 millimeters cloud droplets, mist droplets, drizzle droplets, until the very large, the largest big actual raindrops, right up to 5 millimeter in size. So normally in wind-driven rain simulations, we would focus on two extreme, the very light 0.5 millimeter raindrops and the very large 5 millimeter raindrops. This would give us an indications of the deepest wind-driven rain penetrations from the 0.5 millimeter small raindrop size, because the smaller the raindrop size, it is lighter, so the wind can blow these small raindrops further inwards into the building. So the deepest penetrations, the deepest wind-driven rain penetrations into a building will always result from the smallest raindrops. So it will wet the floor, but it will not likely cause a ponding issues. On the other end, if you have direct rain penetrations coming from the very large 5 millimeter raindrop sizes, then once it penetrates into the buildings, it would very likely result in the ponding of the water, right? There is limitations of wind-driven rain simulations, and it's mainly the following. For wind-driven rain simulations, we will focus primarily on direct penetrations, and we will not account for the rainwater accumulations. We will not consider the rainwater splashings on the facades and then the runoff of that along the facades, landings on the ground levels. We will not account for the splashings and runoff. So we basically assume the rainwater, once it hit the ground, it just disappears. But it will leave a mark where the rain hits, where it hits the ground, and that is your penetration depth. And then from there, we can do some estimations on the rainwater accumulations rate. Okay, I want to briefly talk about the difference between rain return periods and wind return periods. They are two completely different things. The chart on the right is actually the Singapore Public Utility Board, PUB. It's a published data from Singapore PUB on the drainage sizings. So for drainage in Singapore, it has to be able to withstand 100-year rain return period conditions. So that means that for a given return periods, these curve lines, the y-axis is the rainfall intensity in millimeter per hour, versus the x-axis is the raining duration times in minutes. So if we are talking about the highest 100-year return periods, these different combinations will always translate to the same return periods, starting from 130 millimeter per hour rain intensity, and if it rains for 1 full hour, 60 minutes, that amount of rains is considered a 100-year return period. But for example, if you have a super heavy rains of 320 millimeter per hour, basically this 320 is for me to extrapolate this red dotted line, and I extrapolate that all the way to hit the y-axis, and that's where I get the 320. So if this one rains for just about 2.6 minutes, this would also translate to a 100-year return period. Just to give an idea, because these data are from Singapore, so I'm using a Singapore Changi Airport as an example. From 30 plus years of NEA collected data, NEA stands for National Environmental Agency of Singapore, the meteorological agency at Changi airports, where it first used, the mean rain intensity is only 6.7 millimeter per hour. So it doesn't seem very high. That, of course, that is just the mean rain intensity. The highest recorded is 146. We round that up to 150 millimeter per hour. So that is what the most extreme rain intensity recorded at Changi airports. Now, a few months back in July, in China, in Zhengzhou city in Henan province, that horrific flooding situation. So from the news, we realized that in 1 hour, the rain intensity recorded is as high as 200 millimeter per hour for 1 hour. So if we were to plot that point rain intensity in this particular chart, so by Singapore standards, I'm not saying by China standard, just by Singapore standard itself, this 200 millimeter per hour for 60 minutes of rain, you can see that this blue dotted point is located far outside the 100-year return period. And that really tells us how severe that rain condition is. Right, in Singapore, in Malaysia, because we're in the tropical country, so this chart already accounts for our tropical environment, which has a lot of rains, close to 3,000 meters of rains, accumulated rains throughout the whole year. And in China, in the inland area of China, they might not be using this tropical standard chart as their standards. So to them, this July 20th rain, that is why the news agency, they all call it is a 1,000-year return period conditions, right? So that gives us an idea how severe that incident really was. Okay, so why am I mentioning this rain intensity? Because at different rain intensity, the distributions of the different size of the raindrops are different. So in this particular study, conducted by University of Kansas, my alma mater, what the study concludes is at different rain intensity, you can see the x-axis, the raindrop sizes versus the percentage of these distributions, statistical distributions. The heavier rain intensity corresponds to larger portions of the raindrops being larger raindrop sizes. I mean, that makes sense. I mean, if we look at it, if we have a very light conditions, then most of the raindrops are mostly of a small raindrop diameters. But if we have a super strong, super heavy rains going on, then most of the raindrops obviously will be composed of a large raindrop sizes, right? So this gives us the distributions. And using this distribution chart, for example, this 150, this column right here, if you can see my cursor, if you sum up all these percentage numbers, at the end, it will give us 100%, right? So these are basically the percentage distribution charts. So we mainly, in the wind-driven rain simulations, we will look at just a few droplets, the 0.5 millimeters, the 5 millimeter, and maybe another one raindrop sizes in between, whether it's 1 millimeter or 2 millimeter in sizes, right? Okay, so these are basically on the methodologies of the wind-driven rain simulations. I will quickly talk about the passing criteria or the human perceptions on wind-driven rain results. Now, just now I talked about earlier on that BST was involved in these research programs funded by Building Construction Authority of Singapore. In 2005, that joint multi-party research project is to develop natural ventilation CFD simulations methodologies by MGBC of Singapore, thermal comfort criteria by National University of Singapore, and BST comes in on the wind-driven rain simulation methodology guideline and criteria, together with the Eindhoven University of Technologies, TUE from the Netherlands. So at the end of this research project, 2-year research project, item 3, that is what gives the passing criteria of the wind-driven rain study. So it focused on different types of non-residential buildings, for industrial buildings, for healthcare buildings, commercial atriums, hawker centers, sports facilities, and schools. In schools, meaning primary and secondary schools primarily, with natural ventilation classrooms. So it gives us an indication what the human perceptions, what the human tolerance level is on penetration depths. We break it down into different levels from very good. Of course, very good will have the smallest penetration depth, and very poor has the highest penetration depth. Right, so this is the result from that 2-year study. So this, you can treat this as the passing criteria from the wind-driven rain simulation results. You have to have a wind penetration depth less than these requirements. Then the frequency of occurrence, you can treat that as the input parameters you will put into your wind-driven rain simulations. Just now we talked about a 12-month return periods. For certain different types of buildings, yes, you can use anything greater than 6-month return periods, or for certain facilities is 12-month return periods, something like that, right? So the results of that study give us 2 big results. One is for the passing criteria, one is for the input parameters into the wind-driven rain study. I'll give a few case studies on what you can get out from this wind-driven rain simulation. So just now I talked about the Pudo area. I'm going to use these school buildings. That school buildings has a Pudo area, it has a foyer areas. So you can see that this Pudo canopy is a double volume height. So we will first do a natural ventilation CFD, and this is the velocity contour plot I talked about just now. Dark blue stands for low wind speed. So in these 8 different wind directions that we analyze, you can see that the east winds, under east winds, we have a lot of wind rushing inwards into this foyer area and also the Pudo area. So potentially, this would mean there is lots of rain penetrations. So from the natural ventilation results, then we will inject the raindrops. So this is top view. We can see how the rain penetrates into not just the Pudo area, but also into the foyer area. And the penetration depth into the foyer area, you can see from the top view is 3.2 meter. And then in the section view, section B view, you can see the rain angles at about 47 degrees. So that is the kind of result we can get out from the wind-driven rain study. And this is for the smallest raindrops, 0.5 millimeter in size. If we go to the largest raindrops sizes, then yes, the penetration depth is very little into the Pudo area. Most likely is considered acceptable, and there isn't any things into the foyer area, right? For the school, same projects, case study 2, focusing on the Lingway area on the right-hand side. So you can see if we do a section CC at the Lingway, you can see that at the higher floor levels, typically for school buildings, it has multi-floor levels. So we have at the higher floor levels where the wind is stronger, then likelihood that there will be wind-driven rain penetration. So it has a 31 degrees penetrations angles and 51 degrees. So at this lower roof level, pretty much the entire width of this Lingway is wetted. And obviously that is a no-no lah. If I were to run this and I get this kind of simulation result, this is not considered acceptable to me. Then I would advise the architects, your facade treatments, it needs to be enlarged to give more protections. Right. For a high-rise residentials, for a lift lobby corridor area, then at the highest few levels, normally that is where the wind is the strongest and you have rain penetrations inwards. So this gives us an example. At the highest level, that would be always the most critical floor levels with the rains coming in. You can see this rain from the 0.5 millimeter raindrops. It is actually traveling upwards. So now we are tying this back to the velocity contour vector plots we show that near towards the highest of the buildings, the wind is traveling at an upward angle, and that is why the rain, especially the very small rain droplet size, is also traveling at an upward angle, and it will penetrate into this common corridor lift area, and that is where the penetration depth is very severe at about 9 meters. Then at lower floor levels, penetration depth is less, and certain floor level and below, there is no penetration depth. So this is the kind of result we can get out. For larger raindrops, the penetration depth is less. You can, so this is the kind of result we are getting out from the wind-driven rain simulations applicable to residential tower blocks. So from here, from the penetration depths, using the raindrop distributions based on rain intensity, we will be able to figure out, say, at level 24 and 23, we have significant penetration depths from the 1 millimeter raindrops and 5 millimeter raindrops. So we can mathematically estimate using all these informations I talked about previously, to calculate what is the final values, rain accumulation rates, say in liter per minute or liter per second. That is the amount of rainwater accumulations rate. So from here, that would help with the sizings of the scuppered drains and put in some gradients on the floor surface to make sure the water, it does come in, it will flow towards the scuppered drains, and to incorporate slippery resistant surfaces, to apply slippery resistance materials to the surface, right? To make sure that the lift door, typically the solution is the lift door to be slightly raised, elevated to prevent rainwater flowing into the lift core, because we know that after constructions, probably the constructed floor surface gradient is not that perfect, so maybe the accumulated water will flow towards the lift core, and obviously that is a big no-no. Right, so another example is that outdoor refreshment area I talked about. So I have 3 ORA zones located near the ground level of these commercial buildings. And then the green colors are the vertical panels. Right, so you can see that the winds, you have a lot of wind rushing in, and this is the penetration depth. So for certain areas, you can see that when my cursor is pointing, there is a small gap and the wind is allowed to flow through. So because of a very high wind speed flowing into this gap, so there is rain coming in. If there is no wind going into the building, then there is no rain penetration. Right, so from here, coupling the wind speed result with the rain results, we basically can conclude that certain common corridor areas will have some rain penetrations, but the 3 ORA areas would remain dry, basically. So to the developer, this kind of result is considered acceptable. So they just need to make sure that the floor surface, the gradients of this common corridor, it is slightly sloped outwards so that whatever water that comes in will flow away from the buildings and it will not flow into this, for example, these particular gaps. Right, the last case study, just now I talked about the industrial buildings with the fixed facade. So some might have single band louvers, some will have double band louvers. So in this case, if we were to run a very extreme wind speeds of 24 meter per second, a very extreme wind speeds. This would correspond to a very high return periods, but with a double bank louver, you can see that the double bank louver is able to protect even a very high wind speed conditions, direct penetrations. You can see that the wind that eventually guts through the gap, the wind speed is all above the red color. So if the outside wind is about 24 meter per second, then the wind that gets through, if it gets inside the building, it is also a very strong wind inside. But even with such a strong winds, with the double bank louvers, there is no rain penetrations into the production area. Then on the outside driveway area, because it does not have a double bank louver, it only has a parapet wall, then obviously, yes, rain will come in. That's understandable. Okay, so with that, I end my presentations. We can go to the Q&A sessions. If everyone have any questions, you can raise it up. I'll try to answer them to the best of my ability.
Okay, thank you very much, Mr. Ken, for a very insightful talk on the wind-driven rain. Ladies and gentlemen, please leave us your message if you have any questions, and Mr. Ken will try to answer the questions. Let's see. Okay, we have our first questions. What would you say is the accuracy of this sort of simulations? This has been verified on the site post CCC to compare it against a simulation result?
All right, on the accuracy of CFD simulations or accuracy of wind-driven rain simulations, the methodology adopted comes basically from academia, right? Especially, for example, the wind-driven rain methodology. That is the results from that 2-year research project BSD was involved with, together with the Eindhoven University. So you can say in one sentence, the simulation, the accuracy of the simulations is well proven by academia. Now, if someone were to say that, what about if we compare that to site measurements? We don't do that normally, is because just now, like I say, the inputs into these simulations, whether that is return periods for wind-driven rains or the annual average wind speed for the normal natural ventilation, these are based on process results of the entire years or entire 5-year periods. So we are just using an annual average wind speed. So if you were to conduct a site survey to make your site's measurements relevant to CFD, you have to mount your measurements for 1 whole year minimally. Then you can get an apple-and-apple comparisons. If you only mount your instruments for just a few days or 1 month, that is not a representative enough results to compare with CFD simulation results.
I see. Just my own question. Do you have any planning to conduct such a long periods testing to verify your simulations?
It will be difficult. I'm not to say it's not doable, but it's difficult. Actually, in about more than 10 years ago, one of the BSD research project with HDB, with BCA, is we are mounting the measurements at those completed but not yet occupied HDB blocks.
I see.
Right, but back then, because there's I think that's before 2010, so we have to have computers placed as a data locker to record the data. The data won't be transmitted wirelessly, and because uncompleted HDB blocks, there is really no electricity supply, so we have to bring in car batteries and to switch the battery once every few days or something. So it became a logistical nightmare to do that kind of simulations, and even for that, the entire durations of the on-site measurements, if at most, it's just a matter of weeks as well.
Mm.
And if you happens to conduct that measurements during a period where there's not a whole lot of wind, then you are just don't have a good luck to getting a lot of high wind speed measurements out from it. So unless, basically in summary, unless you put the measurements for 1 full year to get good enough representative measurements, if not, I would say the result is not that realistic.
Okay, noted. We have our second questions. Is the wind-driven rain simulation study being used in Malaysia oftenly? What is the demand?
I have some Malaysia wind-driven rain projects. But compared to Singapore, not as many. I would say that probably the topic of this wind-driven rain simulation has not really gaining a lot of steam in Malaysia. But I would say that there are a few inquiries over the last few years. I received a few inquiries on that. They are really showing interest, especially those commercial building PUDO areas, where likely they have received quite a lot of feedbacks from the people saying that PUDO areas it's not dry during raining time, something like that. Yes, so I have got a lot of inquiries on that, but the amount of projects that really require wind-driven rain simulations, yes, they are, but not as many compared to Singapore.
I see. I believe certain awareness need to be raised for the Malaysians to be aware about this kind of service and how important this wind-driven rain can help the building to be more resilient to the natural events. Okay, we have our third questions. What are the challenges you face with using the simulation to tackle wind-driven rain issue into buildings?
That's actually a very good question. Okay, just now I mentioned in my slides, typical mitigation measures for passive systems. I mean, if it is an active system, I think that active system can solve everything. But for a passive system mitigation measures, that means that whatever you put in, say that for a high-rise condominiums that you have horizontal canopies with some louvers of a given size, but say that I need a certain sizes of louvers or horizontal canopy, but whether that size of your facade elements, will that be allowed will that be allowed by other government agencies, say the bomber, fire safety? Because for high-rise buildings, if you have certain facade elements placed out there, that might negatively impact the dispersions of smoke in the event of fire. So for Singapore, taking Singapore as an example, if let's say that we propose facade elements, we have to meet, number one, the fire safety requirements. Fire safety engineers will have to conduct fire CFD to make sure that to help with the waiver applications, because whatever we propose for tackling the wind-driven rains likely will already result in a non-compliance of the prescriptive fire codes, and therefore fire safety engineers will have to come in to fight for the waiver. So it is, and then also for Singapore, if your facade elements, say the horizontal canopy gets too large, then the Singapore URA will impose a GFA penalty. And of course, to developer, GFA is money. They would definitely not pay for the GFA just because for the sake of rain protections. Right, so these are all the different agency conflicting requirements. And in Singapore, there are talks between Building Construction Authority, BCA, URA, Urban Development Agency, the Fire Safety, SCDF, and inter-agency talks to sort of trying to come up with common compromise guidelines so that whatever you do for once, it will not cause non-compliance to the others. But this is still ongoing, the discussions. Right. So that's number one. Yeah. Then the second challenge that I can foresee is this kind of wind-driven rain simulations that it takes a rather long time to complete the study. For example, the base runs, you have to build the 3D geometry, you have to run different wind directions, you have to inject the raindrops. Now, if you have multiple blocks, each block you have to inject the raindrops to each block. So the whole process for the base simulations would probably take around four weeks, a month. Then say another mitigations, the result is not satisfactory, you will to rerun, and then each rerun likely will take another 2 to 3 weeks. So the entire duration of the study is quite long, and that also translates to high fee. And then that high fee likely would discourage the developer from undertaking such a study during the development stage. Right.
I see. Okay. Let's see, is there any other questions? We do not have any other question from the floor. So I think it's also due to the time constraint, we might need to end our webinar today. So thank you very much, Mr. Kempo, for sharing your experience on wind-driven rain with us today. Before we end our webinar today, we'd like to promote some of the Malaysia GBC upcoming events in November. On the 17th November, we have a pocket talk on Maypai Sustainability Initiative. On the 18th of November, we have our Malaysia GBC webinar on sustainability, rethink conventional construction. On the 24th to 25th November, we have Malaysia GBC, IUS GBC 2021, Leadership in Sustainability Defying COVID-19 Conference. Well, ladies and gentlemen, that's the wrap up for our afternoon today. Thank you very much, Mr. Ken. And on behalf of IGN and Malaysia Green Building Council, we thank you for all making your time busy schedule to join us this afternoon. It's been a great pleasure to host this event, and I wish you all safe and a pleasant day. Goodbye. Thank you.
Thank you.